is the equality that is shown here true? Is this equation correct? Can we prove it? As you can see, we have e to the pi, then in the exponent we have pi multiplied by square root of, then the whole thing keeps repeating. Under square root we have again e to the pi, again in this exponent, pi is multiplied by square root, and it keeps going on forever. It's a very interesting infinite expression. So how can we solve this? Let's consider that maybe we can refer to the whole thing as an example to just the unknown value x that we need to find. So this is equal to x. Now consider that right after in the first exponent e to the pi, and then pi multiplied by square root, right under the first square root, it's as if we have the whole thing repeating itself again. So this whole thing under the first square root is another representation of x itself. So this is x again. Therefore, I can effectively write that the unknown x, which is the whole thing, as I said, is equal to e to the pi, and then square root, and x. So can we solve this? Okay, obviously we can also write this in the form of e to the pi, x to the power 1 over 2. Okay, so let's make the assumption that we can represent x in the form of just e to the I theta, in which I is just the well-known I equal to rad minus 1. Okay, so can we find a theta? Theta is our variable. Can we find a theta that solves this problem? And if so, can we find a real value for x? Because we don't want to end up with an imaginary value. The outcome is supposed to be a real value, -1. Okay, so let's substitute this into our equation. So if we do that, x is e to the I theta equal to, here we have e to the pi, and then we have, instead of x, I theta to the power 1 over 2, which becomes e to the I theta divided by 2. Okay, I'm going to use Euler's formula. So the famous Euler's formula, so let me put it this way. So the famous Euler's formula is saying, as well known, that e to the ix, so e to the ix is equal to cosine x plus I sine x. So here, and if to avoid confusion, doesn't matter if you say iz and then cosine z sine z. Okay, and this is I. All right, so in this case, my z is theta over 2, e to the I theta over 2. So if I use Euler, so let's refer to this as equation 1. If I apply equation 1, I get e to the I theta, the left-hand side of this equation, is equal to e to the pi, and then I am applying Euler to the exponent, this portion, which becomes cosine theta over 2 plus I sine theta over 2 in the exponent of e. Okay, so if I want both sides of this equation to be equal to each other, you can see that, so let's further expand this so that it can be easily seen. Okay, so I'm going to further expand this. You can see that I'm saying e to the I theta is equal to e to the pi cosine theta divided by 2 plus I pi sine theta divided by 2. Okay, so we can see that the exponent on the right side, it has real part. So there is a real part, and there is an imaginary part. But on the left side, we have only imaginary part. So as a result, given the target equality we are chasing here, we understand that the real part of the right-hand side should be equal to 0 in order to get to some equality. So, and the imaginary part of the right-hand side should match the imaginary part of the left-hand side. So therefore, we are saying that theta, or let's put it this way, we are saying pi sine theta over 2 is equal to, that's the imaginary part of the right-hand side, is equal to theta. Okay, can we find a theta that's satisfying these two requirements? Okay, the first guess obviously is, since we need cosine theta over 2 to become 0, since we need the whole thing to be 0, from here we conclude that the first answer, for example, is theta equal to pi. Because if we do that, then cosine pi over 2 is 0 and we get it. But then what happens if we feed that into theta for the second equation? We get pi sine pi over 2 equal to pi. That's great because sine pi over 2 is 1 and that matches. So yes, this is a good solution, theta equal to pi. So in that case, since we started with saying that x is equal to I theta as a solution for the equation we targeted, therefore we now understand that x equal to I, x equal to e to the I pi, I substituted theta in equation, let's say 0 here, so there, and then I got x equal to I pi, which is -1, of course. So that's one distinct solution for this problem, which is interesting. Now, to sort of visualize what we are seeing here, I have plotted the real part and imaginary part of outcome. If I what are these two plots? The top is, let's start from the x-axis. The x-axis here is the input to the equation y equal to e to the pi rad x. I know we are chasing, what is the thing we are chasing? We are chasing whether we can have x equal to e to the pi rad x, which we found the answer. I'm just trying to highlight what we are observing visually. So in this case, x-axis is x, the input which goes under the square root. And you can see that for values above 0, for x here, so for values above 0, the output y exponentially very quickly increasing. As soon as even x is on the order of, let's say, close to 0.4, 0.5, y is already on the order of 6, 7, and it goes very fast. So there is nothing we can do about it. The line you see here is line y equal to x, these dotted line, this dotted line here, this one. So if you zoom in, you can see that it's crossing the curve or the plot at -1. So when we have x value as negative values, as you can see on the x-axis, applied basically to this expression or equation under the rad, we get, of course, as a result of that, we get a complex number in the exponent. And as a result, y, or the outcome, is not a real number, it's a complex number. As you can see, there is a real part and there is an imaginary part. So this one is real part of y. So this is real part of y. And this is imaginary part of y that is plotted for the same x applied. So as expected, when x is positive value, the imaginary part is clearly 0. As expected, when you apply positive value at the input under the square root, y becomes just a positive value. But as soon as we start applying negative x values, as you can see here, so anything less than 0, then not only we have some real portion or real for the outcome y, not only we have some real part, but also we have now, as clearly seen here, non-zero imaginary part. But for the unique value of x equal to -1, there is an interesting thing happening. When x is -1, it just turned out that the value of the imaginary part of y for x -1 turned out to be exactly 0 again. There you go. 0. So for unique value of x at input going under the square root as -1, output y becomes a real value again, pure real. and the value of the y is actually -1, as you can see here. If you extend this, you will see that output is exactly -1, and no wonder that this point of -1, -1 happened to be exactly on the dotted line of y equal to x as expected. So this is a graphical visualization that y -1 is the answer to this sort of equation. If you try other negative values, you get to the point that, of course, for example, for x equal to -4, again, the imaginary part of y becomes 0. But the problem with that is not useful for us in this case, because we are chasing this part. We are chasing this question, or the answer to this equation is, while for x equal -4, the imaginary part is again for y 0, but the real part is not -4, is actually just 1. So it's not helping us, because it means that when we feed x in this equation, when we set x equal to -4, y becomes 1. And it's sort of obvious, because in that scenario, what happens is we would say y is equal to e to the pi rad -4, which is e to the pi rad 4i squared. I squared is -1, and becomes e to the 2i pi plus minus, which is exactly 1. And it's not surprised that we are seeing exactly the outcome for real part of y being 1. So we apply x equal to -4 under the square root, we get output y. So input-output not matching, while we wanted input-output to match in order to solve the equation. So the only solution to match input-output is when we set x equal to -1, as shown here. When we set x equal to -1, we clearly get imaginary part 0 and the real part -1. So -1 goes in, -1 goes out, as was proven in this explanation that I provided before to officially find the value of x equal to -1. I hope that this example and the visualization presented here is useful and helpful.